Hi there, my name's Nigel Bayliss. I'm the Optimizer Product Manager, and the purpose of this presentation is to introduce you to Oracle's automatic indexing. And so I'm going to cover the features that are in Oracle Database 19c, and then we'll move on to some important enhancements that we've added to Oracle Database 23c. At the beginning of this deck, I'm going to start off with with a recap of indexing concepts, and then we'll dive into more of the details. So first of all, the goals of automatic indexing. The key point of this is to reduce the manual overhead of maintaining a system at optimum performance over time. Generally speaking, a database requires a degree of ongoing effort because things change over time, like data. The schema may change over time, and that's often due to things like changes in business requirements, and database workloads themselves change, again, almost certainly driven by business requirements and service level requirements, things like that. This does tend to require quite a high degree of skill, and you'll see why in a minute. I'll cover some of the reasons why managing indexes is not entirely straightforward. So the idea behind automatic indexing is to identify candidates and validate those and verify them, and make sure that the candidates that it discovers are in fact beneficial to the workload. And it's not a theoretical benefit either. It's not an estimated benefit. What we want with auto indexing is for it to actually figure out and test the workload and figure out and absolutely prove, if you like, that the indexes themselves improve the performance of the application as a whole. Bear in mind, another thing that we decided to do from the outset was to make sure that it could be used in environments where you already have indexes. So there can be pre-existing indexes, and that's absolutely fine. Automatic indexes will work around those. So work around them and with them, if you like. So there's no issue there. And bear in mind, this feature is available on Oracle Autonomous Database and Oracle Exadata. So what are indexes for, and when should you use them? So I think, so I came up with this little spectrum, if you like, the pros and cons of indexing. And I think the thing that would probably spring to mind is that indexes give you super fast SQL statements. That's one of the sort of fundamentals of what indexes are for, and it's what we tend to think about when we create an index. How can we make a SQL statement faster? But if we stay on that pro side, the benefits, that does have knock-on effects, because if queries or SQL statements run very efficiently, they reduce the amount of resource that is consumed on the system. So that has a knock-on benefit in reducing the cost of resource consumption, if you like, on the machine. And from that, you will get improved scalability, because the platform will be able to support a greater business transaction load, for example. So the key thing really at indexes are to give you greater scalability, give you more efficient resource utilization on the machine to allow you to do more work. So I think there's way more to it than just faster SQL statements, if you like. And that benefit is enormous. I mean, indexes used correctly definitely is able to transform a workload from something average to something incredibly fast. Now, like everything, of course, in life, there's a cost. So if we move to the left-hand side and look at the con side, indexes consume space. They are structures in the database. They consume space. The amount of space is very, very dependent on the system and what it does and what indexes you have, of course. But it's not unusual to see systems where 20, 30, 40, 50% of the space in the database is actually consumed by indexes. So they're not for free, so to speak, in terms of space. But perhaps a more important consideration is that they do increase DML resource consumption. So what I mean by that is, if the data is inserted, updated, deleted, we have to manage the indexes as well. This is all done transparently, so the application doesn't need to do anything special. But there is a cost associated with changing the blocks in the index, and so that has to happen. So as you increase the index count, it can have an effect of increasing the amount of resource that that write activity generates or uses. And then the sort of things in the middle are more sort of general things that are less obvious, I think. So if there is sometimes a temptation to over-index, I call it over-indexing, but what I really mean is that the indexes aren't really optimized. So they tend to be kind of become a sort of medicine for the database, and you throw lots of indexes, individual column indexes, say, at the database, and you end up with lots and lots of indexes. And that does make optimization more difficult in theory. Well, it can do, because you're giving the optimizer more access paths to get the data. And that can mean that you don't necessarily have such a stable SQL execution plan anymore for your queries, because it considers many different types, many different indexes to access the data that you're looking for in the query. So that can have a tendency to make plans change much more often than they would normally. And that can lead to, if you like, a very sort of not a consistent performance from your queries. So you see queries that take different amount of times at different days, for example. So you don't want to over-index, let's put it like that. And also there are decisions to be made, like, should I index column A, B, and C, or can I create an index that just that covers A, B, and C using a single index? So do you use lots of multi-column indexes or many more single column indexes? So it's a decision that's not easy to make. And the other thing really with indexes as a whole is that the performance benefit you get from them is very dependent on the specifics of the workload. So you can see from this that, is your database more read intensive or is it more write intensive? So these are the kind of things that will affect how good or bad the indexes are performing on an individual system. So these are things that are difficult to define sometimes or measure. So that makes the whole process of figuring out what indexes you should and shouldn't use can be quite a challenge, for sure. The other thing that I think that you almost certainly all aware of, that as the application lifecycle moves on, the effort and the risk of making changes to indexing becomes higher. There's more at stake. So what we'd love to be able to do is to create a good set of indexes that will last forever at the development stage. It's easy to do, low risk, everything works very smoothly. But will those indexes that you've chosen there carry through to production and beyond? That's a question that's very difficult to answer further on. So generally speaking, there is often a lot of index changes that do occur further downstream. And as I mentioned, it tends to be ongoing. So in a production system, making changes to index is much more risky and tends to require more effort. And I think another effect that you do tend to see is indexes tend to be added, but there is a definite reluctance to start removing indexes. So you can become overloaded really with indexes and lose sight of which ones are really giving a true benefit. And when you add one, it may be making another index entirely redundant, but that's going to then remain there consuming space or affecting the performance of DML. But there's no, how can you drop that index? How would you know that you should be able to? It's that kind of thing that makes it tricky. So if we look at a traditional approach, what a database administrator might do today, Oracle does provide advisors. So you can use these to analyze your application, your database, and it will give you advice about the kind of things that you can do to alter indexing, for example. The downside of these is the onus really is always traditionally been on the DBA still, and maintaining the balance between these things. So they need to still validate whether the proposed changes from the advisor do make sense, whether they are, should be something that may have a negative side effect, like DML I'm talking about, checking whether The structures that you've changed do remain useful over the long term, and whether to repeat this process. For example, you're going to run the advisor. When do you do it again? Do you do it once a year or 6 months? Or those kind of decisions have to be kind of factored in. And as I said, it tends to be a continuous process because things change in the database. That's, the change is the only constant, as they say. That's, I think, the key thing you're always having to deal with. So let's take a look now at automatic indexing. This feature is available for Oracle Autonomous Database and Oracle Exadata, and it's all of this that I'm going to talk to you about. The next bit, it came in with Oracle Database 19c. So automatic indexing, I guess this is almost an old school term, but it's an expert system that essentially takes the role of a performance engineer or analyst and would make the kind of decisions a person like that would make. It identifies candidates first and foremost, and then it validates or tests those before implementation. So in other words, it figures out what indexes look likely, but then it has to validate that. The whole process is entirely automatic, so there's no manual intervention required. You can just leave it to go, keep running. And the other thing you do have, the activities that it undertakes are audited. So that's stored in the data dictionary. And for example, there's a report you can generate, which will tell you, for example, all the workload queries all the workload SQL statements that were executed and tested and the effect that the indexes have made on those. So it's very fine-grained information, basically. So if we look at the cycle itself, as a capture, we capture the workload SQL. I'll explain how that's done in a minute. The next thing we do, we identify candidate indexes. Essentially, from the workload, we figure out what indexes are good candidates. Again, I'll go into how we do that. Then next is the verification stage, where we verify whether those candidates are good or not. And the way we do that is to test execute workload SQL statements. So we physically build the indexes. They remain hidden during this process so the workload doesn't see them. And then we can run our workload queries on them and work out whether they're improved in performance or not. So essentially, that's the decision phase next, where we decide which candidates are of benefit. And then we make those visible, and then they are exposed to the workload. Then the workload can use them, and then we're done. And then the monitor phase essentially is going to, you kind of start again around the cycle, because this is continuous. The monitor phase will make sure, for example, that indexes are being used, and over time, if they're not, they do get purged away. So we also manage the decommissioning of indexes as well. How does it work? So how does the database figure out what indexes you need? The first thing I would say in summary is it's driven by the performance of your workload SQL statements. That's what drives it. So we can come up, and the database does come up with ideas about what indexes are going to be useful. But the key thing to do once that happens is actually say, well, let's prove that these candidates work. Now, the first thing you need to be aware of, the first component in this process that you need to be aware of, is the automatic SQL tuning set. This is an infrastructure component, as we call it, which is similar to, say, AWR, in that it's something that's provided in Oracle 19c Enterprise Edition, something that you can use if you wish to. So you can turn it on in Oracle Database 19c if you wish. The whole point of it is to collect application SQL statements. So over time, it will essentially capture everything. There are some exclusions. So if a SQL statement doesn't have a plan, we're not going to capture it. We throttle SQL statements that are the dynamic type, where they have where you're using literal values rather than bind values. That's throttled. And then any SQL statement that isn't executed for 53 weeks is also purged as well. So we essentially have a forget mechanism. It does take space in sysawks, so you need to be aware of. So in the table space sysawks, the data dictionary, this information is stored in there, and it really looks like a very conventional SQL tuning set. So you can, query it from the data dictionary, look at what SQL statements are in there. It's all very visible, but that is maintained by a task that runs periodically and essentially keeps that maintained. So it's critical that that is running with automatic indexing. It relies on this infrastructure component, whereas if you want to use it as a repository of SQL history, it's extremely valuable for that. That's something you might want to consider, just using it for that. So you, for example, you have a history of the execution plans that your workload has been using for a minimum of a year or so. So if we look at how it works, and sort of if we start on the left-hand side, database performance repositories are kind of a general label for things like this. So I've labeled the automatic SQL tuning set this. So it has the SQL in it, so we know what SQL the workload uses. Another feature that's been around for a long time, column usage tracking. The database knows what columns you're using in query predicates. And what I mean by that is if you have a query that says where col1 equals 10, we know col1 is being used as against a particular table, and that column is used in a query predicate. Now, that column might benefit from an index. So because you'll be saying where column 1 equals a value, it might be very selective. If you create an index on there, it may retrieve a few rows. So that basically immediately becomes a candidate. What we have to do next is figure out whether it's a good candidate or not, but it's a candidate. Okay. So the candidate indexes are created invisible, and we actually test parse SQL statements from your workload and figure out whether those indexes are going to be used or not, whether the optimizer thinks they're going to be useful. And for those indexes that the optimizer thinks are useful, we will materialize and build them so they are materialized and in the database, but they are invisible. So what that means is that the workload does not see them, does not use them, but we now have them available for testing. So what we can do now is execute the workload itself, some of the workload SQL statements in the background so that they see those indexes. And we can measure the performance then of those queries with, or those SQL statements with or without those indexes. And essentially we then make a decision about which ones are beneficial and which ones are not. And the net result then is to yield an optimized physical database, because the decision is driven by real performance measurements. And so the beneficial auto indexes are then just made visible. So we make those visible, and they are then able to be used then by the workload. So that's the process. On the face of it, it's quite straightforward. The details are quite complicated, of course, but from an overall view, it's conceptually quite simple. So as I say, the beneficial indexes are made useful. If we have built any indexes on the way that are not beneficial, those do after 24 hours revert to being unusable, which means they're essentially just metadata again. Okay. Reporting, as I mentioned, so the process itself, the task itself internally generates data in the data dictionary that you can report on later on. So you can always see the effects. You can always see what has happened when the engine, if you like, has decided to create indexes. All of that is visible to you. Okay, so now for some enhancements beyond Oracle Database 19c. These are quite important, actually. They have a very significant effect, I would say. The first one is now we will include candidates on columns that are used in range predicates. So where we have select something from a table where the column is greater than a value, for example. Previously in 19c, we would only consider candidates that we use, candidate columns that we use in equality predicates. Now we've extended the range of which auto indexes are used to include range predicates. And that, in fact, that's a general point I want to make about auto indexing, because it's an autonomous feature, it will change rapidly. We will make enhancements to it quite quickly. So that's one of the things that's I suppose slightly different to the traditional feature, if you like. This is something that internally is going to evolve very quickly. The other thing that, again, this is incredibly important, is that now we include the DML overhead. So we account for the DML overhead when an index candidate is considered. So we will look at the cost benefit of adding the index, the cost of the DML versus the benefit of the query. We can perform a calculation, if you like, that can offset one against the other. And that leverages the DML tracking, which you may be familiar with, that we've had, again, going a long time back, which tracks the number of inserts, updates, deletes that we have on an object. So the database has this information ready for us to make use of. So it's a nice thing. You know, the way that auto-indexing works is it builds upon lots of features that we've had in the database for a long time. And it's about using that data that's there in a smart way to provide this kind of benefit. Next thing, this is again asked for a lot. So, you know, this should be a very popular addition. So there's support now for function-based indexes as well. And those of you, again, that knows the detail about the insides of the database, that leverages expression tracking. So we, again, the database now since 12.2, I think it was, we included this ability to track expressions that are used in queries. So things like upper surname, you know, where you've got things like where upper surname equals something, for example. Those kind of queries, those are can benefit drastically from function-based indexes. And because we track use of expressions like that, we're able to again evaluate function-based indexes now. The other thing that was added, again, this is really driven by customers. You know, customers are wanting improvements to the feature. So again, that's another thing about autonomous features. There's a lot of activity around them, and there's a lot of very rapid development based on customer experiences and what customers want. So definitely we receive the message loud and clear. It's necessary to have table level includes and excludes. So in other words, you can now target individual tables and say, I don't want auto indexing on these. And so that you can imagine the type of scenario where a database has got a core of it really where tables are very hot, where there's a lot of transactions, data coming in, data being modified. Those particular objects you don't want auto-indexing to look at. Previously, you were able to exclude schemas, but that was deemed too coarse. You wanted something that was much more specific. So we've added this table level, the ability to exclude, or you can positively include specific tables if you want. The other thing is slightly more subtle, but also important, is non-blocking reparse. So what that means is when indexes are exposed to a workload, for example, that will invalidate queries, because the likelihood is, of course, they'll get a new plan. So what generally happens is a query is invalidated. And previously, that would cause essentially a block while we were waiting for that query to be reevaluated, while other sessions were going to use the same query. So you could have in situations where it caused a stutter in performance. So that's something that we've dealt with now, so that we make this a non-blocking operation. So the basics of it are that a single session will reparse a SQL statement, and other sessions using it can continue to use the old plan until the new plan is made ready by the foreground that is reparsing it. So it avoids this blocking of multiple sessions when there are invalidations. So it's a nice enhancement now. So to summarize, it's all about reducing manual overhead when maintaining a system. And maintaining indexes, of course, without manual intervention, optimal indexes, and importantly, can drop unused auto indexes if you wish. And in fact, you can allow it to drop manual ones if you want. By default, it does not do that. But if it's something you want, you can add that as well. And key point, it validates indexes by testing the workload. It's not a theoretical calculation or anything like that. come up with candidates, but ultimately the indexes that are candidates have to prove themselves. And finally, it can be used in systems with and without existing manual indexes. So that's fine. You can mix the two. So where you could go next, there is a new live lab for auto indexes. So I created this fairly recently, actually, because there was a pre-existing one that's more Exadata focused. This one I've pointed towards autonomous database itself. So this is the new one. So give it a try. So you will get the chance to get your hands on this, and you can try it out. And of course, I see these sort of labs as giving you some ideas for you can extend and do other things with them. So I think it's a good starting point. So check that out. And then I write articles in the Optimizer blog. So this topic will come up frequently in the Optimizer blog as well, amongst many others. So if you want to check those out, then there's that blog to go to. So I think that's everything from me. So it just leaves me to say thank you for listening. Hope you enjoyed it. Hope you learned something. And thanks. Speak to you again soon, hopefully.